and welcome to this video on identifying the dimension of a vector space. So this video is going to kind of combine some concepts from previous videos, a couple previous videos I've put out, in which you find the basis of a vector space or the basis of a subspace, because you'll see that once you find a basis of a vector space, then you know the dimension. Alright, the dimension of a vector space is simply the number of vectors that is in a basis of that vector space. And of course that's for finitely dimensional vector spaces, which, in all the examples in my videos, we've been looking at finite dimensional vector spaces, 1 dimension, 2 dimension, 3 dimension. Of course, there are infinitely dimensional vector spaces, but that is not for the topics in these videos I've been making. Okay, so let's get into it. First, on the first page, I define dimension. All right. So the dimension of a vector space. All right, the dimension of a vector space V, which is denoted by this notation, dim of V, right, dimension of V, is the number of vectors in a basis of V. Now, if you've been following along with my videos, you've seen that a bunch of we've seen that our Euclidean spaces, R2, R3, R4, etc., R1, just the real number line. I guess I should write that in as well, right? The dimension of R1, or just, R, the real numbers, is 1. And think about that, right? When you think of the real numbers, the way we usually represent the real numbers was with a number line, right? So you would say that a line is 1-dimensional, right? The dimension of R2, right? All the bases of R2 that we've seen, 1, 0, 0, 1 was the standard basis, had 2 vectors in it, right? So the dimension of R2 is 2. Remember, for R2, that was represented by the XY plane, right? It's a 2-dimensional sheet, right? A plane is considered 2-dimensional. And then the dimension of R3, right? Well, again, just think of the standard basis for these Euclidean spaces. The standard basis, right, was made up of the columns of the identity matrix. So this standard basis for R3 has 1, 0, 0, 0, 1, 0, and 0, 0, 1. So that has 3 vectors, meaning the dimension of R3 is 3. And again, this is harder to draw because it's a 2-dimensional piece of paper. But R3 was usually represented as 3D. They call it 3D space, 3-dimensional Euclidean space. And then you can't really. It's really hard to picture any higher dimensional spaces than that, right? Because even when I trying to draw a 3D space, I'm on a piece of paper here, which is a plane. It's hard to picture 3D space even on a two-dimensional piece of paper. So 4D space, 4-dimensional space, 5-dimensional, that'd be much harder to visualize. But yeah, so notice in general for these Euclidean spaces, the dimension of Rn is equal to n, right? Because you can find a basis, right? That standard basis for Rn, and that has n vectors in it, right? So, all right, now something important to note: the dimension of a set with just the 0 vector, right? Remember, that was a vector space. The set with just the 0 vector, right? It's it's non-empty. It's got the 0 vector in it. It's closed under addition. 0 plus 0 is 0. It's closed under scalar multiplication, right? You multiply the 0 vector by any scalar, it's still the 0 vector, and it also satisfies all those other, the 8 other vector space axioms. So the vector space with only the 0 vector it is that vector space. They define that vector space to have a dimension of 0. Now, I know you might be thinking, hey, well, what about the set with the 0 vector? Isn't that a basis for this vector space? Technically, no. Because the set with the 0 vector is not linearly independent by definition. If you set a scalar multiple of it equal to the 0 vector, right, it would have solutions other than the trivial solution. So I guess you could say the empty set was vacuously a basis for the vector space with only the 0 vector in it. So maybe that's why they're defining the dimension to be 0. But you'll see later too, there's going to be videos I'm putting out in the future where this is going to make things mathematically sound and make things nice and neat for us, defining the dimension of the vector space with only the 0 vector in it, the trivial vector space, you could call it. That has a dimension of 0. Keep that, please keep that in mind. And then one other important note. Now, I don't have I'm not proving this in this video, but an interesting result is that every basis of a vector space V has the dimension of V number of vectors in it, right? So all I'm saying here is that, like, and you've seen this in other videos of mine if you've been watching, like R2, right, has a dimension 2. That means that every basis of R2 is going to have 2 vectors in it, right? The dimension of R3 is 3. So every basis of R3 will have 3 vectors in it. Right? And again, you've seen this in previous videos of mine if you've been following. Alright, so all I have for the rest of this is something similar to what I've done before in past videos. If you want to find the dimension of a vector space, you have to find a basis. So I've done this before. You can look up other videos where I've talked about finding a basis for a vector space. So the first few examples I've got are I'm going to be finding the basis for a vector space that's the span of a set of vectors. Remember, the span of a set of vectors is the set of all linear combinations of those vectors, and that is a vector space. And then my last examples are going to be finding the dimension of a space of vectors, a vector space that's defined by an equation, which again I put up a video about that as well in the past. All right, so I'm going to try to get through these reasonably quickly. All right, so here so the instructions for every single one of these examples from here on out is going to be to find a basis for vector space W, then state the dimension of W. Right. So I have S here. That's not W, right? S is a set of vectors, and these are from R2, where they got 2 components: 1, 3, 2, 5, and 0, negative 4. And W equals the span of S, right? Now remember, the span of S is the set of all linear combinations of these vectors. So every vector in W looks like a scalar multiple times 1, 3 plus a scalar multiple of 2, 5 plus a scalar times 0, negative 4. All right, So we've got that much. All right. 1 S definitely spans W because W is the span of S. But the next question I would ask is, well, okay, so S spans W. That's one thing we need for a basis. Is S a set of linearly independent vectors? And the answer to that is no. So that's bad. Now the reason is, you can see there's a little shortcut here, and I brought this up in a previous video on determining whether a set of vectors is linearly independent or dependent. If the number of vectors is greater than the number of components in the vectors, then they'll be dependent. Alright, so S is not a basis for W. Now that doesn't mean that there's not some other set of 3 vectors that could be a basis, but you'll see that it's not going to be a set of 3 vectors. So let's do this check for independence. Let me actually write it out instead of using the little shortcut thing. Remember how when you check for independence, you take a linear combination of the vectors in S1. So A1 is a scalar here, times 1, 3 plus, and then A2 is a scalar, times 2, 5 plus A3 is a scalar, times 0, negative 4. And you ask, when is this equal to the 0 vector? Right, 0, 0. And this corresponds to solving a system of linear equations involving A1 and A2 and A3 that would have this augmented matrix. Right? So you'd have a matrix for the system with 1, 3 down the first column, right, the coefficients of A1, 2, 5 down the second column, the coefficients of A2, 0, negative 4 down the third column, the coefficients of A3, then a little bar, and then on the other side, the equal sign where the bar is, you have 0, 0. Right? And as I've said in other videos, again, if you've been watching, if not, don't worry about it. I'm going to say it again here. I'm going to try to solve this, solve for A1, A2, A3. And if 0, 0, 0 isn't the only solution, then they're dependent. But if 0, 0, 0 for A1, A2, A3, that trivial solution is the only one, then they're independent. What we do is we try to put this thing into reduced echelon form, through some row operations, or reduced row echelon form, RREF. You'll see on your calculator as RREF as well. And when you're doing this, when you're performing the operations, this column of zeros is always going to be a column of zeros. This never changes when you're doing this check for independence. Because you add rows, multiply rows by something, add to another row, multiply rows by scalars. These will still be 0 all the time. So instead of writing that that bar and that last column of zeros, instead of doing that, I'm just going to focus on the coefficient matrix. All right, this coefficient matrix. I'm just going to focus on this and putting this in reduced echelon form or reduced row echelon form. And do you notice how the coefficient matrix, the columns of the coefficient matrix are simply the vectors of S, right? So we'll simply make a matrix with the columns being the vectors of S and put it in reduced row echelon form. Now there's, couple rows here. Now again, I usually, if I was doing this by hand, would write out one operation at a time. But I'm going to go and show you on the calculator. Alright, let me clear this stuff. So second matrix, this is 84 plus here. Over to the edit matrix A. The size of this, again, I don't care about this last column. That's always going to be zeros. Just remember that it's there. And I got a 2 by 3 matrix, right? So enter the size, 2 rows, 3 columns. First row is 1, 2, 0. Second row, 3, 5, negative 4. Alright, then let's get out of here, go back to the main screen, quit, Then go back to the matrix menu and over to math, and then I want to scroll until I see RREF. Now don't confuse it with REF right above it. I want RREF, reduced row echelon form. Alright, pop that on the main screen. Go back to the matrix and enter matrix A from names there. Alright, so the reduced row echelon form is 1, 0 for the first column, 0, 1, negative 8, and then 4. And then again, you'd have this bar, and then you'd have some zeros over here. Right? Now you see how this would have infinitely many solutions. Right? The A1 would be look at where the pivots are, right? That was a big focus. There's a pivot, right? One of these lead ones in the first column. So A1 would be considered a basic variable. There's another pivot, right? This lead 1 in reduced echelon form in the second column that corresponded to A2. is also what they call a basic variable. And the third column has no pivot, has none of these leading ones in the rows. So the A3 would be free. All right, and this indicates to us, if you want to just do a simple correspondence, this non-pivot column indicates to us a vector that's not necessary. So I do not need to have 0, -4 in this set to span W. Because what you're going to see is that you can set up a relationship, you can figure out how 0, -4 can be written as a linear combination of 1, 3, and 2, 5. So if this vector can be written as a linear combination of these two, you don't need it. So the span of these three is really equal to just the span of these two. Right? And then are these two independent? Well, again, what you're going to notice also, and I've mentioned this in other videos, so I'm not going to go in as in detail as I did before. Look at the pivot columns, right? The columns with pivots, these leading ones in the rows. These correspond to vectors that will be in a basis for my vector space, spanned by S. Right? These are linearly independent vectors, and they would span W as well, right? Again, I don't need 0, -4 because it is a linear combination, and you can show it, of 1, 3, and 2, 5. So look for the pivot columns. So all I'm doing is taking the vectors from the S, the vectors that span my vector space, putting them in a matrix, right, the columns of a matrix, putting that matrix in reduced row echelon form, and looking for what vectors from S correspond to pivot columns. Right, it sounds like a lot, but I've done it in plenty of other videos before. So if we look at the pivot columns, and I'll call this S prime, right, because it's not exactly S, I'm removing a vector, equals, just these two vectors, 1, 3, and the vector 2, 5 in there. This is a basis for W. And you can double check, right? Again, the span of these three vectors would be equivalent to the span of these two. Right? Every linear combination of these three can be written as a linear combination of these two. Additionally, these are independent. Again, that's kind of being brought out from this little system solving and reduced echelon form here with the pivot columns. But you can also double check on your own. Look at, there's two vectors, and remember, a set of two vectors is linearly independent if they are not scalar multiples of each other, which these are not, right? So I have found a basis for this span of S, right? I have found a basis for my vector space W, and this basis has two vectors in it. So based on what I said last page, right? So, again, sorry, I'm going to try to keep this on the same page here. So the dimension of W, right, the dimension of this span of S, this vector space, is 2. And what that means is, since we're in Euclidean space here, we're at R2, that means that W is a plane. So that means this is R2, right? We're in R2, and if I talk about being a plane, that's the entirety of R2. The dimension of W is 2, so W is a plane. I mentioned a plane is a two-dimensional figure. Right? Wonderful. All right, next example. So same stuff, same instructions. So W is a vector space, right? The span of some set of vectors. That is always going to be a vector space, right? The span of a set. I want to find a basis for W, and then if I have a basis, I can state the dimension. All right, so this is again just a bunch of vectors from R2. You have -2, 7, 4, -14, 1, -7 halves, and -6, 21. Now, again, S spans W. that's obvious. That's by definition, right? So 1 S spans W, right? Because W is the span of S. Every vector in W is a linear combination of these 4 vectors. But you'll see that S is not linearly independent. S is a dependent set of vectors for the same reason as last example. Right, so this is good, this is bad. Right? For the same reason as the last example, right, there are more vectors than there are components in the vectors. So it'll be a dependent set. So S is not a basis for W. So what is? Well, we have to find one. So what is? And that's, again, where I'm going to basically say, hey, if I was checking for dependence, right, checking for independence, I'd take a linear combination of these vectors, set it equal to the 0 vector. I'd get this matrix coming back corresponding to that system. So I formulate this matrix where, the first column is the first vector, negative 2, 7, 4, negative 14, 1, negative 7 halves, and negative 6, 21. And then again, there'd be some bar and then some zeros over here. I don't really care about the zeros though. All I really focus, because again, these zeros that would be over here, I'm writing them here, but I won't write them anymore after this. They'll always be zeros, no matter what operations I do. And then I want to take this matrix, this, mostly the coefficient matrix, the left side of the bar, put it in that reduced echelon form or reduced row echelon form. Okay. All right. Well, look at this beautiful thing. This example. If I were to multiply the top row by negative 7 halves and add it to the bottom row, every single element in the bottom row would be 0. The top row is the bottom row, or the bottom row is the top row times negative 7 halves. Hopefully you can see that. So I would do that and 0 out the bottom row. And then the top row, to get it in reduced row echelon form, have a leading 1 in that pivot position. I'd multiply everything by negative half, so it'd be 1, and negative 2, and then negative half, and then positive 3. And then again, there'd be zeros over here. I don't care. Right? So do you see, again, there'd be infinitely many solutions. There are, 3 free variables here. Right? And only A1 would be only the first scalar would be basic. The second, third, and fourth scalars would be free. So that means, okay, that there would be a way to write every single one of these as just a scalar multiple of negative 2, 7. And can you see that? Right, every single one of these vectors that correspond to the non-pivot columns can be expressed as just a multiple of the one with the pivot. Right, there's a pivot, that lead 1. So this one's important here. These I don't need. The ones corresponding to non-pivot columns, but the one corresponding to the pivot column, I'll keep that one. All right, and check it out. Right, this times negative 2 would be that. This times negative 1/2 would be that. This times 3 would be that, right? All 3 of these vectors are just multiples of the first one, so I only really need the first one. So what we're seeing from all this is that the set with just the vector negative 2, 7 in it is a basis for W. Right? Again, it spans W, right? Because all the linear combinations of these 4 can be just written as a multiple of negative 2, 7. So the span of this set is equal to the span of this one vector. And it's obviously linearly independent, as we kind of get that from this matrix setup here, but you can also see that it's a single vector that's non-zero. And any set with one non-zero vector is linearly independent. So it spans W, linearly independent. It is a basis for W, and therefore the dimension of W is equal to 1. And remember I mentioned one-dimensional stuff earlier. That means if I were to look at this, these are all vectors in R2, so I could picture them. Go to GeoGebra or whatever, but I just didn't feel like setting that up right now. Sorry. Like I have in other videos. So if I go to R2, right, the two-dimensional plane, and look at the span of all these vectors, every linear combination of these vectors, or in other words, every multiple of negative 2, 7, I'd trace out a line. Remember I mentioned that earlier. One-dimensional objects are lines. W is a line. And it would be a line going through the origin. Alright, but I'll just say it's a line. Alright. One-dimensional figure. Great. Alright, and I'm doing the same stuff pretty much for these first examples involving spans. Alright. So I've just got one more like this, where I'm in R3 this time. Alright, R3. So again, here S is the set of 3 vectors, all have 3 components, right? 3 vectors from R3. And I'm asking, and W is the span of these vectors, right? So W is made up of all the linear combinations of these 3, a scalar times this, plus a scalar times this, plus a scalar times this. And I'm asking again to find a basis for W, find a basis for the span of S, and then state the dimension. And then maybe even describe the thing, right? Like it's a line or a plane or whatever, a 3D space, a 4D space, 5D space. Obviously, it can't be a 4D space. This is only R3, but you know what I mean. I hope. All right, so I'm just going to jump to the matrix thing. All right. Set up that matrix with the 1, 2, 1, the 5, 0, 0, and the negative 3, 4, 0. And again, there'd be a bar. There'd be 0 if I was checking. If I was checking these vectors for independence, there'd be zeros on the other side or whatever. But I really don't care about that right now. I just go to take this matrix here, put it in reduced row echelon form. And this I'll go to the calculator for just to save on writing, save on a time. So I'm going to enter this matrix. It's a 3 by 3 matrix. This right. 1, 5, negative 3. First row, then 2, 0, 4 for the second row, and 1, 0, 0 for the third row. And then I've already entered up reduced row echelon form, so I can just have that enter again by going to second enter, and there we go. And look, it's the identity matrix. Sorry, 1, 0, 0, 0, 1, 0, 0, 0, 1. And again, there would be some zeros on the other side. So you'd have the first scalar would have to be 0, the second scalar would have to be 0, the third scalar would have to be 0. So if I was checking these vectors for independence, there would only be that trivial solution. So this set of vectors is independent, and it definitely spans W, because W is the span of S. So this is a basis. Right? Look at all the pivots. Right? Every column has a pivot. So this vector, and this vector, right? All the vectors of S do form a basis for W. So S is a basis for W. Wonderful. And then the dimension of W, then the dimension of that vector space would then be 3, because there are 3 vectors in that basis. So W is a 3D space. W is a 3-dimensional space. Right? And in fact, it would be all of R3. Right? This would actually be equal to all of R3, all of that 3-dimensional space, because these are these are vectors from R3. Wonderful. And again, simple as this matrix setup, putting in reduced echelon form, or even just echelon form, right? Because if you put in an echelon form or row echelon form has the same pivot columns that reduced row echelon form would as well. So you can do that if you want to. All right, so now I'm getting into some examples, just a few, where we're given a vector space that's defined by an equation. All right, and asked to find a basis for that and also state the dimension. Same stuff I've been doing, only a little different setup. All right. So here is a vector space. All right, and this is actually a subspace of R2, right? These are vectors from R2. So I have W equals these vectors with, first component x1, second component x2, such that, the second component has to be 0. All right. So again, I'm asked to find a basis for W here. Find a set of vectors that spans W and also the linearly independent, the set of vectors. So look at what each. So first I take if it's a space defined by an equation like this one, just solve the equation for one of the variables, which this is. And if there are any variables on the other side, then those are considered like free. You can choose them to be whatever you want, but there are no variables over here. I just have x2 equals 0. That's it. So let's take a look at what every vector in W looks like. Right? Each vector in W looks like this. You have, some first component x1, some second component x2, but the second component has to be 0. So every vector in W looks like this. So you'd have 5, 0 is in there, -8, 0 is in there, pi 0 is in there. As long as the second component is 0, you're good. You're in W. Well, what do you notice about this? Look at this. x1 is a real number, right? x1 is like a scalar. And each of these kind of technically has a factor of x1. I can pull that scalar of x1 out. And if I do so, what am I left with? I have x1 times the vector 1, 0. All right, so what we're seeing in this line of reasoning here, I am seeing that every vector in W is a scalar multiple of the vector 1, 0. Well, that means that W is equal to the span of the set with the vector 1, 0. Right? Right? Because every vector in W is a linear combination of the vector 1, 0. Right? Or a scalar multiple, right? When it's just one vector, a linear combination is a scalar multiple. Another way to say that, you could say that the set with the vector 1, 0 spans W. So that's one thing you need to check for, right, when you're trying to find a basis. And 2, isn't this set linearly independent, right? And again, you could do a formal check if you wished, use a definition with that equation, set up a scalar multiple of this equal to the 0 vector, and see if it has only the trivial solution where all the scalars are 0 or not. But it's just got one vector, and it's a non-zero vector. Remember, any set with one non-zero vector will be linearly independent. All right, linearly independent, or I'll just write dependent in the future. So these two things are true, so that means this set with the vector 1, 0 is a basis for W. Okay, and therefore the dimension of this vector space W is 1. So W would be a line in R2, right? These are vectors in R2. We're looking on the XY plane or whatever. W would be a line, would trace out a line going through the origin. Right? It's a one-dimensional figure, a line. Wonderful. All right. Next example. And I've got a couple more of these, and they're all pretty similar. Just, vector spaces defined by equations. So here I have a vector space that's another subspace of R2, right? These are vectors from R2 with two components, right? So W equals, vectors with components x1 and x2, such that, this condition satisfied, such that, twice the first component minus 3 times the second component must be equal to 0. Okay. And as I was mentioning before, if we take this equation that defines the space and solve it for one of the variables. So let's say I solve for x1. Say x1 would have to be equal to 3 halves x2, wouldn't it? I would add 3x2, then divide by 2. So this variable x2, I could say, was free. I know we're not setting up a matrix or anything and finding pivots and whatnot. I'm just calling it free because I can let it be whatever I want. I could do the same for x1, but if I let x2 be anything I want, then x1 would have to be some specific number. So like if x2 were 2, x1 would have to be 3. I couldn't let x1 be anything else. If x2 were 4, this would have to be, x1 would have to be 6, right? I can't pick for both of them. I can only pick for one and find the other. So one of them is free. And what you're going to notice is that the number of free variables in these, spaces that are defined by equations is going to be same as the number of vectors in a basis for that space. We'll see that happen. Alright, so as I did with the last one, right, let's take a look at what does every vector in W look like. Every vector in W looks like this. You have component x1, component x2, but we just said component x1 must be 1.5 times x2. So I'll replace x1 with 3 halves x2, and then x2 is not changing. That's the free variable. And then notice both of these components have the scalar x2 in common. So I can call it x2 times, and then the vector 3 halves, and then 1. Right. So what we're saying in this line, what we're seeing is that every vector in W is a scalar multiple of this 3 halves 1. Alright. Now if you'd like, if you don't like the fractions, I could replace x2, and I've done this with free variables before, right? The least common denominator of these numbers is 2. So I could replace x2 with 2t, where t is any real number. Right, because remember, x2 is a free variable. I can let it be any real number I wish. So I can replace x2 if I want with another expression that can take on any real number, right? 2 times t can be any real number I want, depending on the value of t. And if I do that, then we have t times, and then I can multiply these guys by 2 and get 3, 2. Right? So it really doesn't matter, right? Any scalar multiple of 3 halves 1 is also going to be a scalar multiple of 3, 2, right? Just multiply it by 2. Right? Okay, so I'd rather work with this vector. Right, so what we're seeing then is that every vector in W is a scalar multiple of the vector 3, 2, right? So we could say that W equals the span of the set with the vector 3, 2 in it. Or in other words, we could say that the set with the vector 3, 2 in it spans W, right? Every vector in W is a scalar multiple of this. It is, alright, so I'll do this. It spans W, and it's also linearly independent. right? Because it's just a single vector that's non-zero. So this is a basis for W. And if this set with just one vector is a basis for W, then that means that the dimension of W is equal to 1, right? So this is a one-dimensional vector space. And if you think about it, right, a one-dimensional vector space in Euclidean space would basically trace out a line that goes through the origin. Right? So again, W is a line. Right. Cool. All right, number next. All right, my next example. Again, I just have two more. Now we're in R3 though. Okay, I'm working with vectors in R3, subspaces of R3, three-dimensional space. So here, my vector space, so this subspace of R3 called W, is made up of vectors with, first component X, second component Y, third component Z, such that the first component minus 4 times the second component equals 0. Right. Again, I'll solve that for one of the variables. I think it's really easy to solve this for X, right? So we could say that instead of saying that, the first component minus 4 times the second component is 0, we solve this for X and say the first component of the vector in W, any vector in W, is equal to 4 times the second component of any vector in W. Right? All right, so let's take a look at now. Here I can have Y be anything, right? Right, Y is free. You could also say X was free, but they both can't be free. Right, one of them is free, the other one's basic. Because if I can let Y be anything, like 5, but then X would have to be 20, right? X can't be anything else I want. Now look, there are 3 variables though. In this equation, I can let Y be anything. In this vector, I can let Z be anything. Right? Z isn't even mentioned in the equation, so Z could be anything as well. Z is also free. So Y is free, and then Z is free, because again, these are 2 values, 2 letters I can replace with any numbers I want. All right. So what we're going to notice here is that a basis for this is going to have 2 vectors. It's going to have a dimension of 2, I promise you. Right. Well, again, I'm going to go through it the same way I've been doing. Let's look at what these vectors look like, right? What does every vector of W look like? Every vector of W looks like the following. You have a three component vector with first component X, second component Y, third component Z. And I mentioned before that the first component has to be 4 times the second. So I'm going to replace X, that first component, with 4 times Y. And again, Z down there doesn't change. So you see how the vector now has 2 variables in it instead of 1? 2 free variables, two letters I can replace with anything I want. Alright, and then since there are 2 variables, what I'm going to do is I'm going to separate. I'm going to write this vector as a sum with one vector involving the y's and the other vector involving z. Right. So this is equal to the sum of the vector with the y's. You have 4y in the first component, y in the second component, and there's no y, so 0 in the third component, plus, and then a vector involving the other free variable, right, involving the z's. There's no z, so 0, 0, and then there's 1z down here, z. And then looking at this first vector, you see there's a scalar of y in common in all this. I pull that out. Y is a scalar, y is a real number, times the vector 4, 1, 0, plus, and then these all technically, there's 0 z's here. These have z's. You can pull a z out, times the vector 0, 0, 1. Okay, so what we're seeing in this line of reasoning is that every vector in W is a linear combination of these 2 vectors, 4, 1, 0 and 0, 0, 1, right? Every vector in W can be expressed as a scalar times 4, 1, 0 plus a scalar times 0, 0, 1. So another way to say this is that, W is actually equal to the span of the set with these two vectors in it. All right. Or we say the set with these two vectors spans W. But not only does it span W, but it's also linearly independent. Now I know there's not just one vector this time, but another shortcut, if a set has only two vectors in it and they're not scalar multiples, which these are not scalar multiples of one another, then the set of vectors is independent. Now be careful with shortcuts, all right? Because if you have a set of 3 or more vectors, then you're gonna like in earlier examples, you're gonna have to set up that equation where you have a linear combination equal to the 0 vector, and then check if it has the trivial solution only or not, or others. All right, so then that means that this set here with two vectors is a basis for W, and therefore the dimension of W is 2. All right. So W is a two-dimensional vector space. Well, a two-dimensional vector space in terms of Euclidean spaces is a plane. Right? So W is actually a plane. Right? And if you were looking in R3 and were to graph all this out and whatnot, picture all these vectors, you'd see this like sheet, right? A two-dimensional sheet cutting through a two-dimensional sheet cutting through three-dimensional space. That two-dimensional sheet would be representative of this space W. Great. And then one last one. So another vector space that's defined by an equation. So again, here I have vectors from R3, which are ones you can actually picture. Go to some website and do 3D graphing or whatever, GeoGebra. So every vector in W is looking like this. You have first component X, second component Y, third component Z. But then the only way you can be in W is if this relationship holds, right? So all the vectors in W have the first component plus the second component minus 5 times the third component equal to 0. All right, so again, I can take this equation here and solve for one of those variables. All right. Say x equals 5z minus y. All right, so again, now this equation actually does involve all three variables, unlike the last example. You see x equals 5z minus y. The z and the y are free. You can let those be whatever the heck you want. I can let z be 1,000 and y be -2. But then x would have to be 5,002. Right? Once you pick the values for these two, x has to be fixed, right? So x is basic. And that actually accounts for, x is basic, y is free, z is free. That accounts for all three variables. So I know that a basis for this is going to have two vectors in it, right? Because there's two free variables. So this is going to have a dimension of 2 again. This vector space is actually going to be another plane in R3. All right, let's see that. All right, so now instead of writing out all the words like my last examples, I'm just going to say here's a vector in W. Looks like this. You have x, y, z. But we said that the first component x has to be 5 times the third component z minus the second component y. Right? So I'm replacing x with 5z minus y. And then the second component y, third component z. Right, so again, you see the only variables left over are y and z, the two free variables, just like in the last example. And because there are two of these variables, I'm going to again separate. I'm going to rewrite this vector as a sum, one involving y's, one involving z's, a sum of two vectors. So the first vector involving y, you got -y in the first component, y, and then 0 right? No y, plus, and then the vector with the components involving, part of the components involving z. You have 5z in the first component, no z in the second component, so 0, and then just z in the third component. So I'm getting y, pulling the y out of the first one, times the vector -1, 1, 0, plus pulling z out of the second one times the vector 5, 0, 1. And so what we're seeing is, and I'm just going to save myself some writing here, let's just finish this off. Every vector in W is a linear combination of -110 and 501. Alright, so W is the span of the set of these two vectors. So the set of these two vectors spans W, and they're not, these two vectors are not scalar multiples of each other, so they're independent. Okay, so this set, the set of vectors with -110 in it and 501 is a basis for W. And therefore the dimension of the vector space W is 2, right? The number of vectors in a basis. And then, since we're in Euclidean space, we can describe it. W would be a plane again, right? A two-dimensional vector space, a two-dimensional space in Euclidean space is a plane. Wonderful. And it would be a plane containing the origin from R3, right? Everything, all the vector spaces, the subspaces of Euclidean space, will contain the origin, will contain the 0 vector. Great. All right, so lots of stuff going on there. All right, just really take away from this, just I'm doing the same stuff I had in previous videos on, finding a basis for a subspace. The only difference is now we've mentioned the word dimension and it had meaning. Because I had mentioned dimensional, like, R2 is two-dimensional Euclidean space. I mentioned that before without even really, we didn't have the definition of dimension yet. But now we do, right? The dimension of a vector space is simply the number of vectors you see in any basis for that vector space. All right. So I hope you have fun practicing problems related to this, and thank you very much for watching.